Hello, welcome back. So next up we've got Lukas, who I'm honoured to say is a friend and former colleague and a beautiful man in all respects, and a fine practitioner of mobile VR who's going to tell you all about optimising for mobile VR. So take it away.
Thanks, James. Following that up will probably be very disappointing with this talk. But anyway, yes, practical advice for optimising mobile VR. And to very briefly explain who I am, I'm the former lead developer at Opposable VR. I'm now actually a freelance VR developer. I've worked on a huge range of projects for a wide range of clients, both on mobile and desktop. But really today we're talking about one specifically, which I'm going to Alt-Tab out very briefly, just to show the video, if I can. Oh, God. Back. I'll use full screen that. But yeah, so I worked on this project. You may remember I actually talked last year about a sort of broadly similar topic about optimization with mobile VR. And when I did, that was actually before we were very early stages of making Adventure Time, which is the biggest mobile VR project I've worked on. And so when giving that advice, I felt a bit hollow. Like I hadn't really been through the thing properly. You know, I felt like a bit of an imposter. But now I'm back today, recently, after having made this, and basically I can now reinforce that advice with actual evidence, and also sort of, you know, there's other lessons we learned throughout the development process of it. So I'm going to skip on because that video is quite long. Back to no preview. Yeah, there we are. Sorry. Yeah, and view. Sorry. Present. That's what present. How do I view? View. Slideshow. Yeah. Sorry. Yeah. Thank you. Sorry, yeah, bit of faff. I won't go back to that later. I was planning to. It's all about the graphics. As I said last year, and I'll say again this year, it's all about that. So if you think about what we're tasking a mobile phone to do, which in the days of cardboard was any mobile phone, we're basically asking it to run a 60+ FPS performing game or experience. But especially with the cardboard side, actually, that wasn't the end of it for us, where the whole ecosystem of mobile is designed to be efficient, both in battery life and heat, but VR, by the very nature, is very performance demanding. And so we'd run into issues where basically the mobile sort of firmware or hardware would throttle because it got too hot. So we'd have a 60 FPS performing game for 10 minutes, say, and then, you know, that then would dive as the clock speed of the GPU and CPU would be slowed. And so we'd end up with like a 45, 40 frames per second game. So not only did we have that issue, we then always had to manage the heat increase and try and mitigate those problems as much as possible. I mean, fortunately, these days with Daydreams and Gear VR, those problems are mitigated much, much better. But in the days of cardboard, that was a nightmare and one of the hardest things we had to deal with. So before I go into the specific points about, you know, like general points of graphics optimization, I think it's really important to consider about how you design with graphics optimization. And I'll illustrate, and basically with Adventure Time, we learned quite a lot about this, and there's a specific thing I took away most of all, which was you really have to design with graphics optimization like roots in mind. And I'll take a really bad example of this actually, which was in Adventure Time, where in the glider flight game, the player starts, like you see a big expanse ahead of you, you're flying in the air, you can see infinitely in distance like you would in a plane, and sort of see all the dynamic objects ahead of you. Now on paper of the design, that sounds quite fun and interesting, but graphics optimization has not been thought about at all, in the sense of there's no way we can contextually introduce graphics optimization without compromising the user's expectations. And so if we slightly redesign that and say, well, we can keep the glider flight aspect, but just enclose it into an enclosed space, like a cave that can have walls, a cave that can have big objects blocking your view, there's room for graphics optimization then. We can put in occlusion culling, and we can limit the draw distance, for example. But that's up for all members of the team to be discussing together, and you have to sort of work as a team to state those things out as soon as possible, really, so that you can actually incorporate graphics optimization easily later. So once you've gone past that stage of, say, you designed the game, whatever else, and the gameplay you want to do, you'll probably next think about the visual style. Now this was meant to be a GIF, but I was going to show this in Google Slides and have now had to show it on a PDF. But anyway, it doesn't really matter. Basically, the point being, your choice of visual style can have an implicit overhead before you've even started like programming the style itself. So for example, if you consider two sort of routes you can make your game in, so say you wanted a photorealistic, like militaristic look, well, that's going to be quite tricky to do because not only, and again, it comes to the expectations and the overhead generally, where the user's going to expect, for example, high resolution textures, dynamic lighting, maybe like expensive shaders and processing effects, which we're working with a very limited pool of resources. And what's then even worse is the fact that, again, if you want to try and get these savings later, go through an optimization phase, you're limited in what you can actually optimize without sort of compromising what the user is expecting. But say with Adventure Time and the cartoony style, the expectations are so much more open, so much more up to the user. You can basically, like in this example, we made our own lighting system in the vertex and fragment shader and completely ignored the lighting engine entirely, which there's a few compromises, like for example, the objects don't cast shadows onto other objects, but who cares? The user has no frame of reference to compare it to. The user doesn't overly notice. I don't think many users particularly care about it. It looks cool, it looks great. And so that's what I'm talking about an implicit overhead. You've got to be really careful with your visual style. Before I move on to the next sort of point I was going to talk about, I wanted to very briefly talk about batches and draw calls for those who don't really know much about them. A draw call is basically a message sent from the CPU to the GPU, which then the GPU renders a bunch of vertex information in it. But the problem with draw calls is that they're slow, but they are necessary evil. You have to have a draw call, otherwise nothing will render. And so the optimization process of that is you try and have less draw calls with more information in to make that process as efficient as possible. But and so yeah, there's a bunch of ways that these are handled, like in engines. Like for example, Unity has static and dynamic batching, which will basically group objects that should render the same and render them as a sort of larger, in a larger draw call essentially. And fortunately, today, they're becoming much easier to manage. Like in Adventure Time, there's a lot of issues that we had to really carefully manage them, and they could be introduced very easily. But thanks to now, like Daydreams and Gear VR having single stereo pass rendering, and what I think is actually the more important, or one of the more important features that Unity itself has added recently, called GPU instancing. And I'll sort of slightly explain that more with this example. So basically, I would have said about 6 months ago, actually, the selective use of dynamic objects, any dynamic objects at all, you had to be really careful about. And these now, fortunately, I can say new objects, which is so much better. And I think about the savings for Adventure Time using these techniques would have been absolutely ginormous. But anyway, let's take an example here. So you've got like these 3 animal types, and I've stolen these from the Unity Asset Store. So they're just basically the game they're involved with is like a zombie-like game. So these animals, zombies, sort of walk towards the player, trying to attack the player, basically. Now, like if you're an artist and you're trying to design that to make it look pretty and interesting, you might go with this approach where you might have different animal types, for example. Now that looks great, it looks visually appealing, but it's not the most optimal way from the graphics side, again, in terms of saying, well, we need to really limit our batches and draw calls. And I'll show you almost like what could be the alternative, which is essentially to say, well, let's use maximize the potential of GPU instancing. And so you can use that technique to basically share mesh and still have individual elements be different, but you can draw them in the same batches, and you can control the individuals' differences with the use of material property blocks. Now that's a really cool feature, and I'm showing two very contrasting examples, and I suspect, if the team were to come together, you'd probably go somewhere in the middle where you say, well, let's have 2 animal varieties, for example, but use this technique on top to add variety to those animal types. But my point being is that you don't even have to make that decision at this point, but it's about having the ability to sort of iterate up and down in terms of the what performance you're going to need, and having like the compromise you can go to if you need to later, but keeping all those options open. The next technique I want to talk about is occlusion culling, and I say occlusion culling, but it's also more just about using information you know to control rendering as much as you can. So occlusion culling, if I was to more, actually say the theory of, is basically the idea of you only draw what's actually visible to the person or to the camera. So for example, if you had a room that's behind a wall and you're standing on the other side of it, the graphics rendering, like unless you specify specific orders, is actually arbitrary. And so you could theoretically draw the entire room and then find a wall just blocks off all that work that's been done. All those pixels that have been rendered to have been wasted by this wall basically blocking that work. And that's actually a central concept called overdraw. And if you can control overdraw and whatever else, that's really helpful. But occlusion culling is often quite a cheap way where you can sort of manage that effect without having to worry about going too deep into your rendering order. And basically it's the concept of, so you can only draw what you can see. We use this process in actually a desktop game called Salvage, where basically it's basically like a breach and clear game. So you enter into a room, you have to get your soldiers in there, breach and clear the room, and then you move on to the next until you go through like the entire ship, basically. And so I'll demonstrate this example with like a simplified ship schematic, as you can see on my right-hand side. Like in the game, it'd be much more complicated, but for our sake, it'd be easier to see. So like the game begins and the player's in room 1. Now, like you can see essentially like the lines of sight that the player could potentially see. But because we know the room's entirely enclosed off, we don't need to worry about rendering 2, 3, and 4. We can just turn them off or stop the rendering. And that process is a massive saving for our GPU overhead. We might need a tiny bit of CPU overhead to be worrying about it, but basically the game can just sit until it notices something's going to change. So for example, player 1 then wants to move into the second room. We then might say, we need both of them active briefly as they transition from one to another. But then when they enter the room, we just turn off the others again. Like we turn off the room we're just in. And it's a really simple process of just using information you know about to control rendering, rather than implicitly relying on or hoping that rendering processes will work as you might hope they would. But with all this, nothing's off limits. There are so many efficiency savings we had to make. Cardboard as a whole SDK was really not quite ready for commercial use, I don't think, in hindsight. Like just the base SDK example would just throttle and things like that. So we had to try and find every saving. So for example, we would swap static batched objects with dynamic objects when they animated. So like the puzzle path tiles would swap. We even did more nuclear example things. So this is like the big fallback if the performance is low, of actually scaling down the resolution of the image you'd see on the actual phone, on the actual headset. So we take 25% off of the size, and it would actually step down and monitor the frame rate performance. And if it kept going below I think it was like 55, 60 FPS threshold, it would then scale down again and would step down in gradual stages. And we also did a thing where, and we nearly went with it, where we actually took 360 textures, because the player's always in a fixed viewpoint for most of the game. And so we thought we could actually not model anything in 3D, we would lay it out in 3D, take a sort of screenshot, a wraparound screenshot, and then put that on the sphere and not render in real time any of the 3D models. And we nearly went with that, but there was an odd discourse where then the characters would then be introduced, and they'd have to be 3D because they'd move or they'd be active. And it's a weird, it was close, but yeah, you sort of got tricked, and it was a trick, so yeah, for sure. I mean, there's so much more, and obviously it's a quite limited time period, and working out the depth of the audience in terms of how much technical stuff they want. But if you want to talk to me afterwards, then please do. But to generally summarise, as I said, it's all to do with planning, it's all to do with team members working together. It's not just the programmer's responsibility. If the programmer is essentially cast out of this photorealistic rendering style you want and whatever else, his options are limited, or their options are limited in terms of working extra graphics optimization in there. Then it's also then about having fallbacks and options. You need to be able to have alternatives always available to you, and really you should be locking yourself into an option as late as possible. And then when you've chosen an option, you need to be testing as much as you can, really scrutinize. You've got to be checking the frames per second, checking if there is any sort of throttling or drop off after extended use. And if you're finding those things, then yeah, you need to go back to your other options potentially. But there's other ways you can add polish and variety. And so, for example, good sound design, good narrative designs, is a really good way where if you're having to work with graphics constraints, you can introduce polish and extra value elsewhere. But the whole landscape of mobile VR is changing vastly, and this is what's a bit weird talking about it today, is a sense of cardboard seems to be becoming more maligned, and these other mobile VR platforms are becoming the mainstream things now. And I was working in the very worst case scenario, but what I'm hoping is that these lessons you can take away with you, and hopefully make what should be a nicer environment to develop for, make your projects perform and work even better. And that's it. I don't actually have an end slide, but there we are.